everyone.
Good evening.
My name is Bob Bowman, and I coordinate the museums here for the Mound Science and Energy Museum Association. It is hosted at the Mound Cold War Discovery Center and is operated by Dayton History. Commercial's over. But we're very glad you're here. We have a very interesting and timely talk that is about eclipses, because there's going to be a very special one on the 8th of April, which I'm sure Dave is going to put in perspective, and all the other things you want to know or didn't even know you wanted to know about eclipses will be covered. So again, we are going to start now with Dave. I'll give a brief introduction. Dave Bossy is pretty much a lifetime astronomy nerd. I think that would be.
Yeah.
His bio said he got interested in Sputnik in '57, which I was alive then too, but I don't think I crossed the path that far. But anyway, we're very pleased to have Dave to come and explain all the nuances of eclipses. And so without further ado, I want to welcome Dave Bossy. Okay.
Good evening. This is on now. Is this enough reinforcement so you guys in the back can hear me okay? Because I taught at UC for 42 years. The last, 15 or 16 years, I was teaching large-scale classes, 150, 200, 250 students. So I'm used to belting it out if need be. But we got a lot of ground to cover tonight, so I want to get rolling as quickly as possible. We've got a bunch of words up here. And if we could get an understanding of these words, by the time we get down here at the bottom of the Saros panorama, you'll know everything you ever wanted to know about eclipses, and maybe some stuff that you didn't want to know. So, the title of this talk is The Periodicity of Solar and Lunar Eclipses and the Role of the Saros Panorama, which most people have never heard of the Saros Panorama, or even some of these other words. But we're going to run through these and get definitions for them, and by the time we get to the Saros Panorama, it will make perfect sense, we hope. So, we got to talk about our heroes, go back a little bit in time. Theodor von Polzer, I think is how you pronounce his name. Around 1866, he got interested, he was actually a historian, and he was interested in getting calendars from antiquity, various civilizations around the world, and if they had any notations of astronomical events like eclipses, he wanted to get those to kind of calibrate how their calendar stacks up against our modern calendar, so we could put better dates on when events were happening in antiquity. And the problem was he fell down in a rabbit hole and he never came out. And that rabbit hole was using Newton's formulas for gravity and celestial motion, and Edmund Halley added quite a bit on calculating eclipses, and using that information he started calculating eclipses going back in time, all the way back to 1200 BC, and he chased it all the way out to 2161 AD. And I said, okay, he got a little bit past where we are now. Why did he stop? He didn't. He died. So his work was published in 1887, a year after he died, 1886. And it sort of laid around. Nobody was really taking a whole lot of interest in it until a gentleman by the name of Crommelin, Andrew Crommelin. We'll see him in a minute. And he, around 1901, he was doing some work with the Polzer's data. But our real hero is George Vandenberg. Published a book in 1955, at least it was published in English in 1955. It was published in Dutch in 1951. And he spent about 5 years taking Polzer's data and kind of arranging it and trying to get an understanding, a better understanding of how eclipses would be related to one another. And he published a book, which I stole the title from, Periodicity and Variation of Solar and Lunar Eclipses. in the 1990s, Fred Espenak was doing calculations on eclipses, their timing and their locations on the Earth, using more modern mathematical techniques of incredibly high accuracy within 1 second of time, going all the way back in his 5,000 year canon of solar eclipses goes back to 2000 BC and all the way out to 3000 AD. So 5,000 years worth of eclipses, and they're all accurate to within 1 second. And I think he's extended it now. I think there's a 6th millennium canon now. But what I've noticed here is that mustaches and high foreheads seem to be the norm. Because we look at a couple other guys. Oh, here you are. Mustaches and high foreheads. Andrew Claude de la Cherie Crommelin. Where's he from? He's Irish. I don't get it. Anyway, he detected a pattern in the eclipses. There's one pattern that was listed in the vocabulary there to begin with, called the Saros, a period of 6,585.3 days. That the Babylonians knew about that cycle. The Chaldeans and the Sumerians, even before them, knew about the Saros cycle. But he discovered another cycle that's not quite 29 years, it's 28 years, 344 days or something like that. And we'll cover what that's all about. But he was, I had never heard of him before I started doing the research onto this, but he's got a crater on the moon named after him, and he's got a crater on Mars named after him, so he must have been somebody. And then Jean Mies, I didn't bring any of his books along. He wrote a whole series of books. He was a retired Belgian weatherman who his first book was called Mathematical Astronomical Morsels. And they're great little books. Not little, they're this thick. But each chapter, there's like 40 or 50 chapters in each of his books. And so each chapter is maybe 5 or 10 pages long, and it deals with something astronomical or another, just calculating this, that, or the other thing, the altitude of the sun and at the noon, depending on your longitude and latitude and things of that nature. Very interesting reading. But he was a mathematician extraordinaire, and he got together with Espenak. In fact, the 5 millennium canon is listed, both of them, as authors. Mies is still around. He's like 95 years old now? Getting up there. Okay. The animations that I have up here came from Fred Espenak. He put those together, and they're just marvelous graphics. There's other graphics that he put together. He only did these animations for the 20th century and 21st century, so between 1900 and 2100. And I don't know if he's just getting old and doesn't want to do anymore, but he stopped at 2 centuries. But there's a diagram that's similar to this. It's just a still frame of every one of the eclipses in the 5 millennium canon, both the solar eclipses and lunar eclipses. There's about 12,000 solar eclipses and 11,900 lunar eclipses. And it's all online. The Jet Propulsion Laboratory paid for it because they use his data for launching probes to the moon. And the techniques that Espenak was using came from a French guy by the name of Pierre Bretagne, who in the late 70s and early 80s developed an incredible mathematical technique called polynomial sum, where he calculates the position of VSOP 82, as it's called, was the major planets, the 4 inner planets, Mercury, Venus, Earth, and Mars, and Jupiter, Saturn, Uranus, and Neptune. VSOP 87 added a few asteroids, and there was a VSOP 92, which added the moons of Jupiter and some other moons around the solar system. And VSOP is French, so I'm not going to try to say what it is, but it's basically secular variations of the planetary orbits. And using his technique, another couple friends of his, Champron and Champrontazy, calculated the position of the moon. They concentrated on the moon. And using their calculations, their techniques, with the only input is date and time, we know the position of the moon within 1 centimeter. This big. And using VSOP 92, we know the position of the Earth relative to the Sun within a few kilometers. We know the position of the giant planets, Jupiter and Saturn, within, I'll say, 100 kilometers. So it's important work, important data. This animation, you might be familiar with seeing this swoopy thing on any images that you've seen relative to the eclipse. That why is that a swoopy line? Well, it's got to do with the Earth being a sphere, and it's rotating, and it's tilted. Complicates the business. But if you notice, I added a line on here. It's a black line, and the umbral shadow, that little guy right there, follows this straight line. So the moon is moving in a straight line through space, so naturally the shadows will be following that straight line. It's the goofiness of the shape of the Earth and the rotating Earth that creates all these fancy, swoopy lines to try to figure out where do I want to be if I want to see the eclipse. This is the output, or a sample of the product of Espinax data. And there's enough information in there to generate one of these, not necessarily well, you guys, I guess you could do an animation, but certainly the graphics. And it's just a bunch of numbers. And we hate numbers, right? We want to see pictures. Pictures tell us much more than numbers do. There's one number I'm going to keep referring to, though, and that's this number right here called gamma. These are the first 5 lines of the lunar eclipses, and these are the first 5 lines of the solar eclipses. These are 2 separate files. But there's a gamma associated with solar eclipses, and there's a gamma associated with lunar eclipses, and they're kind of the same thing. Kind of. I'll demonstrate what those are. We have our image of the sun. A disk in the sky is how it appears, right? Just a circle in the sky. And we have a disk for the moon. And basically what an eclipse is, a solar eclipse anyway, is the moon passes in front of the sun. And since the sun and the moon are just about the same size, but not exact, we get a total eclipse when the moon completely covers the disk of the sun. But gamma, that number, is a measurement of the distance between the center of the disk of the moon and the center of the disk of the sun at the maximum eclipse point. There's lots of eclipses where, again, if you stay in Cincinnati, this won't make any difference to you guys. You guys just can walk out in your driveway and look up and see this eclipse. How jealous am I?
It'll be cloudy.
It's still worth watching, believe me. It's still worth watching.
Got a car and a full gas tank, I'll see it.
Okay. My original plan was to go to San Antonio, but that 2 days to drive down, 2 days to find and watch the eclipse, and 2 days to drive back home.
We'll go to Boca Chica and see a starship while you're down there.
See it burn up.
We'll see it on the pad.
So there are some eclipses where the moon's motion passes either above the center of the disk of the sun or passes below, but there's a distance between the center of the disk of the moon and the center of the disk of the sun. So when that number gets to be 0, that's a good thing, because that means there's really no distance between the center of the disk of the sun and the center of the disk of the moon. But it doesn't happen ever, or at least it doesn't in the 5 millennium canon of eclipses. The closest one I could find was about 1500 BC, when the difference was, 22 minutes separated the difference between the center of the disk of the sun and the center of the disk of the moon. I'll explain what that time is a little bit later, but it's darn close to 0. But we don't like these numbers. Well, we like numbers, but we want to see what numbers produce. And numbers produce things like this. On the left, we have one of Espinak's graphics of the solar eclipse, actually the April 8th eclipse. And we see that swoopy line. The midpoint of the eclipse is down in Mexico somewhere. San Antonio will be right about there, so I'm not going to be there. But here we are up in under the Great Lakes up here, and we're going to get a pretty good shot at it if the clouds permit. And on the right-hand side, I've got a graphic for a lunar eclipse. What I can say about lunar eclipses is that nothing changes between a solar eclipse and a lunar eclipse. Nothing changes except everything. But it's the same moon, it's the same sun, it's the same Earth, it's the same lunar orbit. All that's different is things are this way instead of that way, things are up instead of down, and left instead of right, so it's basically things are more opposite than they are different. And this is an eclipse from 2033, April 14th. Mark that date on your calendar. This lunar eclipse is tightly coupled with this solar eclipse, and it's not going to be visible from North America. So I guess we won't be able to get to see it. But there are other eclipses that lunar eclipses we'll be able to talk about. The points of interest on these graphics. For a solar eclipse, we have what's called the umbral path, that blue line right there, the two blue lines. That's the size of the shadow as it moves across the Earth. That's the total shadow, the umbra. The penumbra is a partial shadow, like what you can see any place else on the East Coast. You're going to see the disk of the moon miss the center of the disk of the sun by a substantial portion. I think in Cincinnati it's going to be something like 99% or something like 98.9%. So they'll be under the penumbra, not the umbra. The umbra for this eclipse I think is about 110 miles in diameter, if I'm not mistaken. Could be mistaken, but the maximum for any eclipse is 167 miles. And that's basically a whole bunch of stuff has to fall into place for a 167 mile diameter shadow to pass over the Earth. But the penumbra, and I'll have more images of the penumbra and what that's all about, is that partial shadow is about 2,000 miles, a little bit more than 2,000 miles across. So if you're way out here on the edge of the penumbra, near what we would call the penumbra southern limit, you're going to see the disk of the moon just take a tiny little bite out of the image of the sun. You're going to see the moon do something like that. This tiny little bit gets covered up. And the same way at the northern limit, the other side of the penumbra, basically we're going to see the moon pass underneath the disk of the sun. So again, it takes a tiny little bite out of the sun. So we want to be as close to the center line as possible. Would be nice. But anywhere under the umbral shadow, you'll see a total eclipse. The 2 points that when we look at other graphics of other eclipses, then we can decide is that a good eclipse or a bad eclipse. There's this subsolar point marked with an X on each of the graphics. It's that point on the Earth that at the midpoint of the eclipse, the sun is at the zenith. And Espenak, I wish he hadn't done this, but I guess it makes sense for him to do that. A lot of these eclipses are in Polar Bear Town or Penguin Town, depending on how you want to look at it. And to make the maximum part of the shadow visible, he tilts and plays games with the image of the Earth, the twist of the Earth. So we have to pay attention to that subsolar point, especially when it comes to the mid-eclipse point, which is always marked with this little asterisk, little star. That is where the bulge of the Earth is closest to the moon, and thus that's where the shadow would be the largest. So the shadow really does change size a little bit as the eclipse progresses. And when it comes to a lunar eclipse, we're talking about the ecliptic, which is the path of the sun in the sky, or in this case, it's the path of the anti-sun, or it's the shadow of the Earth. The total shadow, the umbra of the Earth, is shown here as a darker area, and in the penumbra, that partial shadow, is quite a bit larger. But the partial shadow is exactly that. It's just partial shadow. If you're close to the umbra, whether it's a solar eclipse or a lunar eclipse, it'll be pretty dark. It's 99% shadow right up against the edge of the umbra. The umbra is 100% shadow, but on the outer edge of the penumbra, we're talking about 1%, 2% shadow. So a partial phase for a lunar eclipse, the moon has to enter and cross over the penumbra to get to the umbra if it's a total eclipse. There are some eclipses where the moon completely misses the umbra and barely makes the penumbra, and then it's I would challenge anyone for one of those kind of eclipses to go outside and look at the moon. If you know there's an eclipse going on, you can go, oh yeah, I guess there's something going on there, but you wouldn't see it just, be that evident to you because it's such a fractional shadow. This is what not to do. Do not, actually, Barron is the only smart one here, right? He's not looking at, I think he might be messing with a pinhole camera down here, which is the way to do it. Melania's got her sunglasses on, but old Donald, he's going to fry his eyes. But the best instrument for observing a solar eclipse is a chair. Forget about trying to take a picture. Take a picture of the people around you. That's much more interesting 5 years or 10 years from now. But to try to get a picture of the eclipse, it takes a lot of practice, which means you have to see a lot of eclipses. And since they don't come around very often in any particular location, you have to go to the eclipse, right? So you're going to be trotting the globe, so to speak, to get the experience of being able to take pictures with a camera. On the other hand, lots of people take pictures, and it's up on YouTube and various other websites. There's lots of places around where you can find images of solar eclipses, and lunar eclipses for that matter. But you want to stand for totality, since any place on the earth that you might be, on top of the mound over here might be a little bit better than way down here. When you're looking at the horizon, the sky you're seeing that comes right down against your horizon is about 200 miles away. And just a few degrees up from that, you're talking about 150 miles away, 140 miles away. And if the shadow is at most 167 miles in diameter, this eclipse is about 110 miles in diameter, so the shadow will be about 55 miles in radius, which is a third of the way to the horizon. So you're going to see sort of like a twilight sky, like just before sunrise or after sunset, all the way around 360 degrees around under the umbral path. And watching an eclipse again, if it's cloudy, you should still be able to see that sort of activity. And you all know about glasses, right? So the solar circumstance, what is the eclipse all about? We got the moon going around the earth somehow, and it's going to cast a shadow, this conical umbral shadow here, and then the penumbra shadow is an expanding cone that will cover part of the earth. But if you're under the penumbra, you're going to see the moon covering some of the sun, but you're going to see a portion of the sun which is exposed. Now I should have taken this slide out. It's basically kind of redundant. It tells us about the umbra, the penumbra. But it does explain, you may have heard in reference to lunar eclipses, the blood moon. Every total lunar eclipse turns red. The moon turns red. Because the earth has an atmosphere, thin though it might be, and it catches sunlight and refracts it, scatters the blue end of the spectrum. The blue end of the spectrum has 16 times the probability of being scattered relative to the red end. So there's still blue light in there, but it's greatly reduced. So the light coming through the Earth's atmosphere just happens to focus about 250,000 miles away from the Earth, and it lands on the moon. So the moon turns red and actually gets brighter than that innermost part of the penumbra. We can see a picture of that in a second. This is what causes all the difficulty. That if we can see the umbral shadow, imagine a plane cutting the Earth in half. We see the penumbra as a circular structure and the umbra as a circular structure. But the problem is, we're on the surface and we're interested in where do I want to be to see the eclipse. The sun doesn't care. The sun says, here comes a shadow, goes across the Earth, and that's the end of the sun's involvement. If we want to figure out where we want to be, well, that's up to us. And that's where things really get complicated. There's, again, another example, 2008, August 1st, an eclipse that, well, it was Greenland and even above Scandinavia, across Siberia up here. Again, this you got to be a polar bear to see one of these eclipses, right? In fact, this one, that was 2015. That you could buy tickets on an airplane, jet plane, that would take off. I think they were running them out of Denmark, and they'd fly out and get ahead of the shadow, and then let the shadow catch up with them, because you know, a plane only goes what 550 miles an hour maybe, and the shadow at its slowest is moving about 2,200 miles an hour. At its fastest at the edges of the Earth, it's moving about 6,000 miles an hour. So they can't follow the shadow very far, but it does get a little bit of extended totality if you want to spend the money and go right on an airplane. But you're above the clouds. There's that. So, pictures of eclipses. Here they are. Only a handful of eclipse pictures that I have. Total eclipses. The moon's disk completely covers the sun's disk and allows us to see the corona. It's the outer atmosphere of the sun. The sun has an atmosphere, and it's very hot, and it's fairly bright, but it's not as bright as the surface of the sun, called the photosphere. So we can only see the corona during a total eclipse, when the moon covers up the photosphere and allows us to see the chromosphere, or the corona. And here's another solar eclipse that looks a great deal different than this one does. And what we're going to have this time, if we get to see it, is going to be closer to this eclipse than this one over here. The difference being this is taking during a solar minimum, or near the solar minimum. You know, the sun goes through an 11.2-year cycle of being busy and then getting quiet and getting busy and getting quiet. When the sun gets busy, it looks like this, and we're about a year away from the solar maximum. So the sun's going to be quite active and has been quite active very recently. But the moon is going to cover up the disk of the sun, and we're going to see who knows what kind of flares and prominences and things coming off of the sun. An annular eclipse is when the diameter of the moon is smaller than the diameter of the sun. So how could that be? Does the moon change its diameter? Well, as a matter of fact, it does, because the moon's orbit is an ellipse, not a circle. So there are parts of the moon's orbit when it's closer to the Earth, and other times when it's farther away from the Earth. When it's farther away, the moon is smaller, the disk is smaller, and when it's closer, the disk is bigger. And so there are times when, even though we might have a gamma near zero, at the center of the disk of the moon just about lays on top of the center of the disk of the sun, it isn't big enough to cover the whole sun. So we see a ring, or an annulus, if you are into Greek, and it looks like that. And it doesn't get dark. We don't see the corona. Some people say, oh, they're chromia eclipses. I consider them to be total eclipses because the gamma value gets close to zero. So it's that gamma value that I'm chasing. And then there are some eclipses that, because of where the moon is on its orbit and the distance from the Earth, plus the Earth has this 4,000-mile bulge around it, so that when an eclipse starts, it might be an annular eclipse because the moon is too far away to cast a shadow all the way to the Earth. And then during the eclipse, the shadow, the umbra path, catches up and touches the Earth and crosses the Earth for a little while. So we have what's called a hybrid eclipse. They start out as annular, they go to total, sometimes they go back to being annular, sometimes they just end as being total. And since the distance between the Earth and the Moon is getting bigger all the time, about 2.5 inches every year, we've only got about 6 million years of total eclipses left. Right now, annular eclipses outnumber total eclipses, and that number as a percentage will continue to grow. Eventually, there will be nothing but annular eclipses. So we live at a good time, sort of, I guess. So now, the lunar circumstance. Nothing changes except everything. We have the Moon going around the Earth. The Sun is occluded by the Earth, and so the Earth has an umbra, but the Earth's umbra is about 4 times longer than the distance between the Earth and the Moon. So there's no probability of any kind of annular eclipse with the Moon. And the penumbra, we have one of those, right? And so the Moon on its orbit has to pass through the penumbra into the umbra if it's going to be a total eclipse, if it doesn't miss. And then we go back into the partial phase again, the penumbra, and then we have to wait another 7 or 10 or 15 or 20 years to see another eclipse. Now, lunar eclipses seem to be more common than solar eclipses, only because they're visible over so much of the Earth. If you're seeing a solar eclipse, you have to be under that umbral shadow. And the shadow passes over your head in anywhere from, see, this is going to be a fairly long eclipse. It's about 5 minutes if you're on that center line. Where you are here, I think I looked at it today, you're about 2 minutes and 5 seconds or something like that coming through this part of Ohio. So we see the angle of the path of the Moon. The Moon's orbit is not in the same plane as the Earth's orbit around the Sun, which is why there aren't eclipses every full moon or every new moon. So the Moon's orbit, if I get this right, this is like one of those puzzles you get at Gatlinburg, right? The Moon's orbit is tilted about 6 degrees. And so we have to be somewhere in this vicinity, the Earth and, or the Sun and the Moon, to have an eclipse. For a lunar eclipse, the Sun is going to be at one node and the Moon will be at the opposite node, passing through the anti-Sun or the umbra and penumbra of the Earth. And that's really a big piece of what I'm going to be talking about here tonight. So, again, using Espinax images, we see the Moon pass into the penumbra, finally makes its way into, they call it a partial lunar eclipse because there's a little bit of the Moon that stays out in the penumbra. It's splitting hairs as far as I'm concerned. Because it looks like a total eclipse. The Moon will turn red, and then it will pass out through the other side of the shadow of the penumbra. The Moon moves its own diameter every hour. The Sun moves its own diameter every 12 hours. So the motion of the Sun we don't really have to talk a whole lot about. But the motion of the Moon gives us some time frame for how long this eclipse is going to last. In this particular case, we're talking about, you can see these numbers. Oh, don't see it on here, but I'm sure it can be calculated. But the eclipse is going to take upwards of 4 or 5 hours if you want to stay up late and watch the whole thing. So the Moon is going to travel a significant area across the sky in 5 hours. It moves its own diameter every hour on its orbit, moving to the east, but the sky is continually rotating to the west, carrying the Moon and the umbra and penumbra with it of the Earth. So what a total lunar eclipse looks like is that the Moon turns red before it completely dims out. Here's one that we can actually kind of see the shape of the umbra right here. Is Steve Grissmiller, the astrophotographer from Cincinnati, he lives in Titusville now, so he can watch all the rocket launches from his backyard. He likes it. But here we can see the phases of the eclipse as we get towards the moon's disk completely entering the umbra, and then it gets a little bit brighter, and then we see the moon turn red, and then moves on through the umbra and begins to move out of the umbra into the penumbra, and finally the eclipse is over. Another kind of redundant eclipse diagram, except this does show the scale. This diagram here, we see the moon and its umbra path just barely reaches the Earth. Sometimes it reaches it, we have a total eclipse. Sometimes it doesn't reach the Earth, and we have an annular eclipse. And for a lunar eclipse, we can see that the moon, the umbral footprint is pretty big, and the moon takes a while, as much as 3 hours, to cross the umbra. Solar eclipses demand that you go to them. This is from Easter Island, where the moon ray, I forget what the local natives were called, but they built these weird statues, and this was an eclipse, I think, from 2010, and sure enough, this October, the shadow is going to pass back over Easter Island again. And Easter Island, tiny little place in the Pacific, gets a second shot at an eclipse. It's going to be an annular eclipse, though. So, and a lunar eclipse, they come to you. You can see the moon rising in eclipse, and as it climbs up, we see totality into this area here, and we move back off to the penumbra, and finally the eclipse is over. So the moon will cover quite a bit of the sky in that 5 hours that the eclipse is going to happen. Here we can see the penumbral effect, and you've seen it all the time, it's just now you know what it's called. The 100% shadow is called the umbra, no matter what it is, shadow of your hand, shadow of the moon. And it's conically shaped because the sun is an extended disk, and obviously the sun is much bigger than the moon. It's a little over 400 times bigger, a little over 400 times farther away, because they're about the same size apparently in the sky. But it reaches back to this point and then starts something called the antumbra, which has got some characteristics of the umbra, that we're going to have a small gamma if we're in here, but part of the sun is visible over the shoulder of the moon in this case. So the antumbra does have sunlight in it. That's where we would see annular eclipses. Here's a diagram that shows a total eclipse someplace out in the Pacific, the umbral path moving across the waters out there, and we can see the umbra, the circle here, or the penumbra I should say, penumbra, and close to the path of totality, the penumbra gets darker and darker because it contains less and less sunlight. This is a picture from outside the geophysics building at UC. I just happened to catch one day. There's a retaining wall here. It's about 3 feet tall. It is casting a shadow on the ground. And the building, which is over my right shoulder, 4 stories tall, actually 5 stories I think from where I am here, it is casting a shadow, and we see that shadow down here. But this shadow is a lot fuzzier. The penumbra is a half a degree in diameter. Half a degree, not diameter, but a half a degree added onto the shadow. So a half a degree on 3 feet is about 1/8 of an inch. So there is a penumbra here, it's just too small to be seen. But from a distance of 50 or 60 feet or so, we can see this fuzzy effect. Where it's the umbra of the building, it's someplace down in here. The penumbra goes out to about here somewhere, and we see this gradient of shadow in between. Now, the circumstances of the eclipses, whether lunar or solar, just depends on, there's a whole bunch of information here, most of which is interesting but not important. What is important is this number right here. The inclination of the orbit of the moon. The moon's orbit is tilted 5.14 degrees relative to the ecliptic plane, or the plane of the Earth's orbit around the sun. The sun is in the ecliptic plane, the Earth is in the ecliptic plane, the moon is only in the ecliptic plane when it's crossing one of those nodes. And the nodes have two names. One's the ascending node and the other is the descending node. So the moon rises above the ecliptic plane for half an orbit, falls down through the ecliptic plane through what we call the descending node, then passes under the plane of the ecliptic and back to the ascending node once again. Okay, now we're getting down to meat and potatoes. The conspirators of the eclipse are these three lengths of the month. You know, what's the definition of the month? Is it 29 days this year? Well, 28 days sometimes for February, or it's 30, or it's
31 for March.
What's that?
31 for March.
31 for March. And basically the sun and the moon do not care about Pope Gregory and Christopher Clavius and what they did to the calendar. I mean, January 1st is such an arbitrary date when it comes to astronomical events and trying to cycle them all together. It's good for counting, but not if you're paying attention to the sky. But I did read just recently that in Roman times, before Julius Caesar corrected the Roman Republic calendar, which had been in place for like 400 years, the first day of the year was April 1st. And it was Pope Gregory XIII who moved it to January 1st. Why, I'm not sure. And the people who kept celebrating the first of the year on April 1st were called April Fools. I don't know if that's true or not, but it sounded good. So we've got 3 different months, and it's how these different month lengths play against one another that creates an eclipse or not, or the variation of eclipses. The synodic month is by far the most important, and that is the month of phases. We need a new moon for a solar eclipse, a full moon for a lunar eclipse. That's it, hands down. So the 29 and a half days and a bunch more, we don't really care about this, but 29 and a half days for the synodic month. And synod just means a time interval, which is kind of a bad name. But it's the month of phases. The draconic month, it measures the time it takes the moon to get from node to node. The ascending node over the descending node, or the descending node around to the ascending node. And it's 27.2 days. It's much shorter. Well, the synodic month has to go around the Earth once, and then during that month of the moon's travel, the Earth and the moon travel about 30 degrees on the Earth's orbit. It's a whole month, right? 1/12 of the year. So the moon has to go 360 degrees plus 30 more. So that's why the synodic month is much longer than the draconic month, the time it takes to get from node to node. And just to make things confusing and interesting, the nodes do not just float in space. I mean, they kind of do, but there's what we call a perturbation of the moon's orbit. The moon's orbit is doing this. It's spinning in space. So the node, as the moon is traveling from one node, say the ascending node, over to the descending node is coming at the moon. So the moon gets there a little early, because it's a dynamic. And I think I'm going to need this other guy here. Yeah. The other month is called the anomalistic month, and that's basically the anomaly. Kepler came up with the term. He considered the orbits of the planets, which is what he was studying, to be circles, except they didn't stay in circles. There was an anomaly of the circular orbit, which Isaac Newton, about 50 years later, said, oh, it's just because the orbits are ellipses. Kepler figured out that the orbits were ellipses, but only by measuring the positions of the planets over a long period of time and seeing that, hey, you know, they're not moving at the same speed, they're not moving at the same distance, something's going on here. They're moving in ellipses. So something akin to this. Not nearly this elliptical. If you could see the orbit of the moon drawn out, you'd say that's a circle. Because there is a 32,000-mile difference between when the moon is closest and when the moon is farthest. But we're playing that against 240,000 miles. So it's a good, 15% change in the distance between the Earth and the moon. The sun and the Earth do the same thing. The Earth has what's called a perihelion and an aphelion. The closest point to the sun is called the perihelion. The aphelion is the farthest point, and it's a 1,000,000-mile swing. But we're playing that against 92 million miles. So it's a very small, about 1.4% change in the distance between the Earth and the sun, which does not cause the seasons. A lot of my students, college students, used to think that, but I straightened them out. But the anomalistic month, which is perigee to perigee, again, peri is the Greek prefix for close, or close to, or close of, and G is the shortened form of geos, or of the Earth. So we have close of the Earth, and the aphelion, which means far, far of the Earth, for perigee and apogee. But for the Earth going around the sun, this is in reference to the sun, so we have a helion. So we have a perihelion and an aphelion. Perihelion is around January 3rd, aphelion is around the 4th of July. So we're farther from the sun during our summer. So again, does not cause our seasons. But it's 27.5 days. So it's longer than the Draconic month because, see if I get this right, the moon is going around the sun, or around the Earth rather, in a counterclockwise fashion. It goes around this way. And the moon's orbit is spinning. There's a perturbation. It's changing, doing this at a certain rate of speed. So the moon has to catch up with the perigee, so to speak. So that's why it's a little bit longer than the Draconic month. The Draconic month is going against the direction of the moon. The anomalistic month is going in the same direction as the moon. And they're all different lengths. And they all get to play a part of the puzzle of generating an eclipse. So our synodic month of phases, there's a full moon. Of course, we know what the full moon looks like. But a new moon, have you ever seen a picture of a new moon? Right there. Well, how do you see the moon? Shouldn't that be an eclipse? If the moon is new and directly between the Earth and the sun, well, it would be if it weren't for that pesky, I can't go back to Gatlinburg or something, I don't know what to do here. If you catch the new moon at one of these high points, there's a 6-degree, 5.1 degree difference between the position of the sun and the position of the moon. So what we're looking at there is just a tiny little sliver of the limb of the moon illuminated by the sun. And sure enough, we've got an image of a new moon. The Draconic month, there's that perturbation of the nodes. So the moon doesn't show the motion here, but we can see that the line of nodes, which is where we have to be for an eclipse, right? The sun and or the moon has to be on that line for an eclipse to occur or close to it. And the moon's orbit is spinning around like this every 18.6 years. Which, again, that's another dynamic that has to get explained. The longitude of the ascending node, this green one right here, this angle right here is from the vernal equinox. That's the first point of Aries, or where the sun was on March 20th. Actually, on March 19th. No, it was March 20th if you were in England. There was about a 4-hour difference between us and in England, right? Actually, about more than 4 hours. And the other argument is this, the argument of the perihelion, or perigee in this case, and that's measured from the plane of the ecliptic around to the point of perigee. So those are the two numbers that are constantly changing, constantly dynamic with the orbit of the moon. Let's take a look at that next here. There's the moon's orbit to scale. You can see it's a circle. It looks like a circle. But there's a significant difference. What is that? 42,000 kilometers difference between perigee and apogee. And that produces these two different images of the moon. At apogee, the moon is this big. And at perigee, the moon is this big. Every now and then, the papers and the magazines and news people always get excited about a supermoon. It's going to be a supermoon tonight. All that means is the full moon happens when the moon is at perigee. Happens every 14 months. So it's not really very uncommon at all. For the sun, again, that very tiny 1.4 degree swing, 1.4% change, at aphelion, the sun is a little bit smaller than perihelion. But here we can see how the moon spends most of its time smaller than any of the sun's images, and only when the moon is closer to perigee do we have the opportunity for a lunar eclipse. And that perturbation of the argument of the periapsis, 8.85 years takes to spin the moon's orbit all the way around. The Earth does the same thing, going around the sun, but its perturbation is about 140,000 years. It takes a while for that to change for the Earth. So, fortnight. You probably grew up thinking fortnight is 14 days, right? Technically, or at least astronomically, it's the time between a lunar eclipse and a solar eclipse in the same interval, or the same period of time, called the eclipse season, which I'll get to in a second. But we can see here in 2023 and 2024, we had new moons. So these are 4 solar eclipses, and for our full moon, we had 4 lunar eclipses. So when the moon gets to one of its nodes, the fortnight, the time in between the new moon and the full moon, only being 14 days, and it's actually 14.77 days, we can see that they occur in pairs, for the most part. Most eclipse seasons, as they're called, will have one solar eclipse and one lunar eclipse. But every now and then, if the spacing and timing is right, we can get 3 eclipses, 2 of one variety and 1 of the other variety. 2 solar eclipses and 1 lunar eclipse, or 2 lunar eclipses and 1 solar eclipse. And I've got some examples of how that has happened fairly recently. But that gamma value that I talked about, I found a much more interesting or much more understandable measurement, and that was the period of time, the hours and minutes, between the midpoint of the eclipse and when the moon was on the ascending node, or when the sun was on the ascending node. So here we're seeing the eclipse is 7 hours and 20 minutes before the node, which means we had an eclipse, and then the moon moves out of the eclipse, and, well, this is a solar eclipse, so it's just a measurement of the time it spent in the penumbra getting to the center of the umbra. For lunar eclipses, again, it's the same value. Here's 19 hours and 37 minutes after the node, the eclipse occurs. So the moon goes through the descending node, in this case, and 19 hours later, it finally gets to the eclipse, which means it's not a great eclipse. That number is less than about 8 or 9, either one of these numbers, plus or minus. That's a pretty good eclipse, total eclipse. And again, the perfect gamma of 0 would be, there would be no time interval between the eclipse, the midpoint of the eclipse, and the passing of the node. And again, looking at all 5,000 years of Espinax eclipses, there was only one that differed by 22 minutes. That was the smallest value I could find. And these lunar eclipses over here, 19 hours, 17 hours, 21 hours, 17 hours, these are horrible eclipses. Because the time it takes to get too far away from the ecliptic path to have a decent eclipse is something like 19 or 20 or 21 hours. By the time you get up to about 28 hours, there's no eclipse at all. We completely miss. So we'll look at these again. I want to get rid of these guys that are just in the noise. So the eclipse time relative to the node passage time. So in 2023, we had an April eclipse and an October eclipse. And then this year, we're going to have an April eclipse, yes, and an October eclipse. This is the one you have to be down on Easter Island to see. Lunar eclipses in 2023, May 5th, October 28th, and we had March 25th. We had a lunar eclipse just a few days ago, right? 2 days, Monday night, but the weather did not permit us to see that. But again, at 21 hours, the umbra is not touched. It's nothing but a penumbral eclipse. And here it's 17 hours. So if we look at these diagrams for those 8 eclipses, and notice how we go solar, lunar, we get into 2024, we go lunar, solar, lunar, solar. So the actual sequence is changing over time as these values, the synodic month and the draconic month slide past one another. And here we can see that our eclipse last year, this is the October annular eclipse. You had to be in the southwest United States to see it. And here's our April 8th eclipse, the umbral footprint going right across the eastern portion of North America. And in October, there'll be another eclipse that passes over Easter Island, which is right out here someplace. And if we look at the lunar eclipses, they're calling us a penumbral because the moon just passes through the penumbra. It doesn't even touch the umbra. Last October, well, it touches the penumbra. We had, it's a partial 77 minutes that the moon spent a tiny little sliver passing through the umbra. We get to this year, March 25th, the one just a few days ago, was visible from North America. If we would have seen it, you would think, well, this is nighttime, right? Now this is showing where the eclipse is visible from on the Earth. So it's visible from North America. But it was a crummy eclipse anyway, since it passed through the penumbra and not completely through the penumbra. We've got our eclipse coming up. Notice we have the midpoint of the eclipse is somewhere down here in Mexico. The subsolar point is down here off the opposite side of the Pacific from the Yucatan. So there's not a good deal of distance between these two, which means it's what we call a central eclipse. These are typically very good eclipses, typically in the central regions of the Earth. And here we have the lunar eclipse this September. Again, it's what, 63 minutes of penumbral partial activity. That's the moon just slicing through the umbra right there. So one edge of the moon might get a little dark, the way you described that. Here's that lunation. We talked about how the moon goes around the Earth, as it does here, but it has to go 360 degrees around the Earth, and then there's this extra portion to get the sun back, or the moon back in front of the sun, so we can have the next potential solar eclipse. And we got our phases that we can explain that way. So it's more than one 360-degree trip, why it's 29 and a half days to get from new moon to new moon, or full moon to full moon, or half that 14.77 days to get from new moon to full moon, or full moon to new moon. The variation in velocity, it's something that Kepler observed and Newton explained, is that when any orbiting body is closer to the body that it's orbiting, it's moving faster than at the opposite end of the orbit. So the periapsis, it's called, periapsis just means it's a generic orbit, a piece of cardboard. I have a periapsis right here. Right? Cardboard just doesn't make any sense. But the moon moves faster on this part of the orbit and slower on this part of the orbit. It averages out to that 29 and a half days, or if we're going from perigee to perigee, it's 27.2 days. That variation in velocity should throw a wrench into things, shouldn't it? Well, the answer is it all averages out. And that 18.6-year perturbation of the movement of the nodes around the, let me take that back, that's the periapsis, the argument of the periapsis. And this is 2 centuries worth of full moons that I put together, time in between one full moon and the next full moon. It's plus or minus 6 hours. There's about a 12-hour swing between the longest lunation and the shortest lunation, only 12 hours. And depending on what kind of time interval you're covering, you can see most of the time it's within a couple hours, plus or minus 2 hours. It's only in very extreme situations where we have out around that plus or minus 6 hour mark. So now this idea of the eclipse season, I really don't like the term, but everybody else uses it, so I have to. I prefer the term eclipse window, because it's only during the eclipse season or during the window that an eclipse can occur. And that's because the line of nodes, the ascending node and the descending node, have to be lined up with the sun more or less. You know, there's this region, a time interval, when an eclipse can occur. And on the opposite side of the Earth's orbit, the Moon's orbit, we have the same sort of eclipse season. And in between, we've got about 5 months of no eclipses. We still have new moons and full moons, but the shadows miss one another. The shadow of the Earth misses the moon, and the shadow of the moon misses the Earth. Here's another diagram. This is a little bit better, I guess, showing how the shadows miss the Earth, but when we have the line of nodes lining up with the sun, we're going to get the ascending node and descending node somewhere in the vicinity of lining up with the sun, and we'll have the opportunity for an eclipse. And this is a goofy kind of diagram which I have to come back to and correct, because it's not, it demonstrates an idea, but it's incorrect in its presentation. It's technical presentation. And that is where we have this little star and this guy here. This is the position of the sun every day moving across the eclipse season, or the eclipse window. And here we have the moon cruising in, maybe hitting the node when the sun is there, or maybe not. You know, it could have the moon is here when the sun is here, and we have a goofy partial eclipse of one kind or another, partial solar eclipse or a partial lunar eclipse. And then the eclipse season eventually ends when the disk of the moon can no longer touch the disk of the sun. And the question here, I got my handy dandy Home Depot eclipse season that looks something like this. We have the node right in the center there, and let's see, I get the yellow guys. This is the sun's path. It's lower and then upper yardstick. No, ecliptic path. Here we have the lunar path, 6 degrees inclined, or 5.14 degrees inclined, and the moon will be passing along here. Now, at this scale, the diameter of the sun and the diameter of the moon is only ½ inch. So you'd say, well, how can this be the eclipse season out here? The moon and the sun just aren't anywhere near one another, if you're looking from the center of the Earth. But if you're a polar bear, you get an eclipse. Or in this case down here, if you're a penguin, you can get to see an eclipse. So where the eclipse is on the planet depends on where in the eclipse season is the eclipse actually occurring. So it's this middle region right in here. This is the hot spot, so to speak, when the moon's disk and the sun's disk are going to be overlaid on one another. And we're going to get what's called a central eclipse, somewhere where the subsolar point and the mid-eclipse point are close to each other on the globe. So an eclipse can occur anytime during the eclipse season, but it's specifically determined by the synodic month, right? That instant of the new moon, that's the solar eclipse. The instant of the full moon, that's the lunar eclipse. And again, that shows how the moon moves across the eclipse season. It takes the sun 34 to 36 days to cross the eclipse season, it takes the moon about 68 hours to cross the eclipse season. So the moon, you got the sun just plodding along, and the moon comes along, zip, and we get an eclipse of one kind or another, depending on how far away from the node did we actually see the eclipse occur. This diagram, this really shows it pretty clearly, where we can have a partial eclipse, or depending on where we are on the globe, where most of the sun is not occluded by the moon because the node is farther along. So it depends on where the sun is in the eclipse season, and when the moon gets there, that determines the eclipse. And here we have a lunar eclipse where the umbra and penumbra of the Earth is much larger than the moon itself. It's about 5 times the diameter of the moon. So here we have the node crossing, and then a number of hours later, many hours later, we have the full moon passing through a tiny little bit of the penumbra. So what does this look like in the sky? I don't know if I have any astronomers in here, or people who are familiar enough with the sky to know where, say, Orion is. Where's Orion? Orion's right here, right? We got Scorpio down here, Scorpius. Sagittarius is right there. And this is the path of the sun, what we call the ecliptic. This is a Mercator projection, so the path of the sun across the sky is tilted because of the Earth's tilt. And we see the sun moving, we just crossed the equinox, which was right here, and we're heading up to June 21st, and that'll be the beginning of summer. This is summer season here. Here's the beginning of fall. We wrap around over here, the beginning of fall. Here's winter, and we go back up to summer here. So spring. We got all spring going on here. But on June 21st, when, say, it's midsummer, when it's actually the beginning of summer, it's going to be a while, and winter's coming back. On December 21st, I sit around saying, okay, good, we got past that part, now spring is coming. It's finally here. But that tilt of the moon's orbit relative to the ecliptic path, so the ecliptic is the orange path, the black path is the moon's orbit, and we can see where they cross. That is the definition of the node. They're approximately 180 degrees apart, but not really. By the time the sun gets from here, moving to the east, gets to here, the node will have progressed because of that perturbation, the movement of the argument of the periapsis, the longitude of the ascending node. So these things are in motion, but as far as the sun being down here and the moon is down here with the eclipse season, we're going to have a solar eclipse. Then the moon moves on its way and gets over to this eclipse season, which is 180 degrees away from this eclipse season. So the sun has moved in here a little bit, and the moon is going to have some sort of lunar eclipse someplace over here. So that's that fortnight effect. Now, if we look at all the eclipses of recent 2017 down to 2024, these numbers of eclipses during a calendar year, in the arbitrary nature of January 1st. Sometimes we usually have 4 eclipses every year, but sometimes there are 5, sometimes there are 6, and once in a very, very, very great while, there can be 7. But things have to be stacked up just right, and what we're really looking for is eclipse season to eclipse season. 2 eclipses in eclipse season, 2 eclipses in the next eclipse season. But we can also have 3. I think I can demonstrate that here. Go back to my eclipse season. Again, it's about 36 degrees. I got 36 inches on here. So here's my eclipse season. My lunation comes along, and most of the time it looks something like this. So I have a lunar eclipse or a solar eclipse right here, and I've got a fortnight later, I've got the opposite eclipse. Say this is solar, this is lunar, and we might have an arrangement like this, where early in the eclipse season we have a solar eclipse, later in the eclipse season we have a lunar eclipse. And every now and then, when the things are stacked up just right, we can get a complete lunation inside of the eclipse season. So that's why we have 2 eclipses. In this case, I've got lunar eclipse and lunar eclipse, and in the middle we're going to have a solar eclipse. So the eclipse seasons that have 3 eclipses, those are the ones we're especially looking for. I'm done with this now. Put that away until 2045. So I've got 36 eclipses in this 7-year stretch. 36 eclipses, 17 eclipse seasons, and per year we can see we got 4s and 5s and 6s. But there's 3 eclipse seasons, or 2 of them, right here in 2018 and 2020. And to have 3 eclipses in one eclipse season, one's got to be really early in the eclipse season when things are spread apart, and one that's got to be late in the eclipse season because we're fitting 29.5 days into 36 days, so it just barely fits. One's going to be above the ecliptic plane, well above the ecliptic plane. One's going to be well below the ecliptic plane, so there's going to be crummy eclipses. But the one in the middle is going to have the sun and the moon very close to the node. So those are going to be good eclipses. And here we can see we have a partial solar in southern Australia, northern Europe, but the one in the middle, total eclipse, South America, Europe, Africa, Asia, Australia. So it covers a pretty good section of the globe because it's not too far from the equator and in the equatorial region of the Earth. And here 2 years later, we got another one, but this one is partial lunar, and the solar in between. It's an annular eclipse, but it's going to be a really nice annular eclipse if you get into them. So we're looking for those every now and then. They happen about every, let's see, 3 eclipse seasons are 11% of the time. So that's about every 5 years we get one of those. And here's a diagram of the way it would look. Here we have the moon too high, too far above the ecliptic plane, so the umbra misses the Earth, but the penumbra just barely catches it, and the polar bears get to see a partial eclipse. So that would look like this. We have a solar eclipse that's you see way down in Penguin Town. Actually, there's no land, just a little bit of Australia. And then in the middle, we've got this really dynamite lunar eclipse where the moon goes right across the center of the umbra, crosses the node, maybe right here, maybe like an hour and a half after the eclipse has occurred, and the eclipse is still going on. And then we end that trio, the triplet of eclipses, 2018, with an eclipse. You can see we're well up into the northern regions. No total path at all. The umbra image or shadow just misses the Earth, and what we're left with is just a little bit of penumbra up in Scandinavia and Siberia. And the opposite configuration we had in 2020, where we have a lunar followed by a solar followed by a lunar, and you can see the 2 lunar eclipses, one on one northern portion of the penumbra of the Earth, barely. I mean, that's just a terrible eclipse. You want to get up at 2 o'clock in the morning and watch it. And here we have this is even a worse eclipse. We can see that the moon just barely scrapes the penumbra. But in between, we've got our subsolar point right there in India, and right up in Mongolia or whatever, we've got the midpoint of the eclipse, and it goes right across the mid part of the Earth. The semester, the time it takes the sun to get from one node of the moon to the other node of the moon. You can say, well, it's half a year, right? No, it's a half a year minus 18 days. Because it's at 18 days, well, to get from one node to the other, it's only 9 days advancing. To get from one node back to the original node is 18 days earlier in the calendar. That's why if you look at years worth of eclipses, year after year, you can watch the eclipses move earlier in the calendar year by about 18 days. There are going to be 2 eclipse seasons in the year, and they're marching backwards through the eclipse, through the calendar. So the sun, here we have 177.18 days it takes the sun to get from the descending node, say, around to the ascending node, the sun here. The moon does that in a fortnight, right? That's all it takes. But the sun will arrive at the node, since the node is moving this way. This is the ascending node moving this way, descending node moving that way. The moon is moving this way in its orbit, so the moon gets to the ascending node a little bit early. The sun also does the same thing, arrives 9 days short of 6 months. And what that looks like on the sky, I'll put the sky against this in a second, the moon's orbit is wobbling like a plate that you drop on the counter, wobbles around, and there's nothing really, there's no friction involved here, so there's nothing to really stop this perturbation. It's actually caused by the sun. The advance of the perigee of the moon is caused by the moon itself, raising the tides. The tides spinning Earth take the tides and push them out ahead of the Earth, ahead of the rotating Earth. So now we've got an asymmetrical Earth with a little bit of additional mass closer to the moon, advanced of the moon, and that accelerates the moon on its orbit, and that's what moves the moon into a higher orbit and advances the moon 2.5 inches every year. And it's just going to keep on doing it. Here, it's the same diagram again, but now I can show the eclipse season and how the nodes are migrating during one semester. It moves about that much, and during an eclipse year, 2 eclipse seasons, it moves about 18 degrees. That's about 9 degrees, it's about 18 degrees, and again, the moon and the sun are moving from west to east, but the nodes are moving east to west, the opposite direction. So finally we get to the Saros. Now this is really getting to the meat of the subject here. That again, the Babylonians knew about this. Thales, a Greek astronomer, 5th century BC, 584 BC, May 25th, predicted an eclipse that stopped a war. The Medes and the Lydians were fighting in Turkey, and had been fighting for decades. And basically, Thales said, if you guys don't stop fighting, I'm going to make the sun go away. They all laughed at him until 2 o'clock that afternoon. They all threw down their weapons and negotiated a peace and ran home. Astronomers used to have clout, political clout. We have it no more. But this period of 6,585.321 days, 18 years, 10 days, 7 hours, and 42 minutes, whatever geometry we've got of the Earth and the Sun and the Moon, it's going to repeat. It's just simple resonance. It takes a while, but eventually we get back to the same configuration. It doesn't have to be an eclipse. Anytime we have some arrangement of the Sun, the Earth, and the Moon, first quarter moon, third quarter moon, whatever it happens to be, 18 years, 10 days, 7 hours, and 42 minutes later, that geometry is going to repeat. So it happens to be an eclipse, the eclipse is going to repeat. And here we see an eclipse from 1981, there's one from 1999, and one from 2017. And this Saros number here is basically the series number that these eclipses that are 6,585.321 days apart. And you can see the similarity in the path of the umbra across the Earth. But wait a minute, there's not the same, continents are not underneath. Well, there's 0.321 days, the 7 hours and 42 minutes. This Earth continues to spin during that 7 hours and 42 minutes. It moves the location of the eclipse 115 degrees farther west. So here we can see the eclipse from 2017. How many people saw the 2017 eclipse? Okay. So you were someplace along this line. Hopefully you weren't anywhere near Hopkinsville, Kentucky, because that's where like 300,000 people were in this little town that got like 30,000 people.
And the thunderstorms.
Was that?
And the thunderstorms nearby there.
Oh, but it cleared up. But the only place that had clouds was out here in Illinois. They had clouds for a little while, and South Carolina had problems. But we back up a number of years, 18 years, 10 days. We find another eclipse in 1999. Go back another 18 years, 1981. We can see a very similar path, but the Earth is rotated a little bit more in between there. But things aren't quite that simple. The resonance is not exact. While we have 223 synodic months, there's no doubt that we have the net number of synodic months because we're going to have that new moon for an eclipse. But the draconic months, where's the node? 242 draconic months to bring the node right back to where it was 18 years ago. But it's not exactly 242. It's 241.999 draconic months. And the difference between 241.999 draconic months and 242 is 39 minutes. So the, see, I guess I'm going to draw this up right here. The exact location of the eclipse, here we can see the path is very similar, but actually the moon is intercepting, the synodic month ends 39 minutes earlier than it did the last Saros. So it was 18 years ago, 18 years, 10 days, we have another eclipse, but it's 39 minutes earlier than it was 18 years ago. And that 39 minutes backs up the eclipse back through the eclipse season. So we're going to have some movement. Showing these two, again, they look very similar. I think when Dean was here, he talked about when he was on a boat in Greece. That's where he was right about there somewhere. And he got to see an eclipse. But here we can see how the umbral path, these two, the animations are not synchronized. They're self-synchronizing. You can see there's a little bit of difference, about 8 hours difference between these two. It's pretty close to that 7 hours and 42 minutes. And just to show that we're not being prejudicial here, lunar eclipses suffer the same consequence. Every 18 years, 10 days, the geometry of the Earth, Sun, and the Moon repeats. So it's a lunar eclipse this time. So we have 1988, we have a lunar eclipse, bad one. 2006, 18 years later, and not much of an improvement. There is a slight difference. Here, May 24, or 2024, March 25th, the eclipse we had a few days ago wasn't worth watching anyway, although we would have been able to see it. Clouds prevented that from happening. And if we look at the solar eclipses, here we have something out over the Pacific Ocean. Here we're back over Africa, and the eclipse over the Mediterranean, and then 18 years, 10 days, 7 hours and 42 minutes later, we have this eclipse that's coming up just in a few days, a week and a half. And just pile some more of these up. Again, one Saros interval separates these eclipses. There's a bunch of other eclipses that go on. It's about 40 or 41 eclipses in between Saros eclipses. And they're, again, all over the place. But they themselves are part of a Saros series that's independent of the Saros series I'm demonstrating here. Again, this is the one there, 2024. This is our eclipse coming up. Oops. And you go back 18 years, you get that eclipse over Greece. And 18 years hence, you're out over the Pacific, 115 degrees farther west. And here we're going to be back over Greece again. Sort of. It's got this a little bit farther south. You look how I draw these lines on here. This is the path of the umbra in space, landing on the globe. You can see they're not exactly the same. And that's caused by that 39 minutes that separates, that the eclipse is early. I'm not going to bother with that. So here I've just, in Excel, just graphed the synodic month, the anomalistic month, and draconic month, starting everybody at 0 right here, and then 6,585 rows later, we have this point right here where the three graphs come back together, all phasing back to 0. And again, this difference between being right on the 0 point, this is the 7 hours and 42 minutes. Some other diagrams, this is the same ones again. Saros after Saros after Saros. 18 years, 10 days, 7 hours, 42 minutes. And same thing for lunar eclipses. 1988, March 3rd, 2006, March 14th, and March 25th, 2024, the one that we didn't get to see a few days ago. Again, separated by one Saros. The exoligmos is just 3 seroi, which is the plural of seros, strung together. So we end up back in the same general longitude area on the Earth. And the latitude is shifting because of that 39 minutes early. So the eclipses are moving, in this case, they're moving up the globe. So they're moving backwards through the eclipse season. So we started out below the descending node, and we're walking backwards, getting closer and closer to a really nice eclipse in the central region, and we continue to march until there's no more eclipses off the beginning of the eclipse season. The exoligmos is just 3 seroi strung together. This is an example of the exoligmos, most interesting one. 1970, March 7th. It was really the first eclipse that I got to see, not totality, because I was here in Cincinnati, but it was about 60% occluded. And then in 2006, there's a Greek eclipse there, and then we go 115 degrees farther west, and we end up out in the Pacific in Indonesia, and we get back to 2024, and we've got pretty close to the same eclipse. So we're in the same general longitude, but the latitude is slightly different. What was most interesting about this eclipse is this is where the CIA and NASA, really in the Air Force, unveiled what the SR-71 could really do. They changed the camera configuration in the nose of the SR-71, and they followed the shadow from the Yucatan all the way up across Nova Scotia and up here. Now the eclipse, the shadow is moving probably about 2,500 miles an hour there. And that's classified, because that's how fast the SR-71 was going, which it doesn't go that fast. No. That's a secret. So here we got a bunch of exoligmos. I'm not sure what the plural of exoligmos is. I'm not going to try it. 1807 to 1861, 1861 to 1916. And you can see, not only are we changing the depth here, we're running out of penumbra. Here we have more total shadow than we have here or here. And again, from 1916 to 1970, very brief partial eclipse. 2024, March 25th, the eclipse that we missed, the moon just passes through the umbra. So the moon's path is moving upwards through the umbra and the penumbra, marching backwards through the eclipse season. Or eclipse paths in 2045, if you're interested in that one. So the tilt of the Earth and the seasons has a little bit to do with changing the latitude of the eclipse. But it's really that backing up of the eclipse backwards through the eclipse season. Starts at the end of the eclipse season and walks backwards. So in this case, we're starting at the North Pole and we're heading southward. We get to our 2017 eclipse right here, which is one of the last ones, but here we see it crossing the United States. We got 2053 coming up, and I think that's the last one on here. Now we got 2035, and then 2053. Yeah. So these eclipses started at the North Pole, and they're moving 115 degrees apart each time, moving southward across the globe, because they're at the ascending node, so the eclipses start above the ecliptic plane and walk backwards down through the ecliptic plane. Again, here's that 1970 eclipse. Exoligmos later, we're coming up with this eclipse this April. And then in 2078, mark your calendars, we've got another one crossing North America. And again, not to be prejudicial, we've got lunar eclipses, so we can actually see the ecliptic path changing throughout the seasons, right? Following that curve, the sinuous curve across the Mercator projection of the sky, if you will. So Saros series, we just take the exoligmos, keep it running. We end up with about 40 or 41 eclipses that make up a Saros series. And again, they're all very similar, but you can see even in this set right here, how far south this eclipse is and how the eclipse is moving northward, eclipse by eclipse. And lunar eclipses, here we're moving into the umbra, so these are getting to be better eclipses. But this is Saros Series 133, which is different than eclipse or Saros Series 136. Lunar Saros Series and Solar Saros Series are numbered independently. But what's the same is, if it's an odd number, the sun is at the ascending node. If it's an even numbered Saros Series, the sun is at the descending node. Now, this is a pretty good explanation of what we're all about. The geographic Earth, that's that spinning, tilted, continent-laden thing that we live on. And we're interested in where is the shadow, not just passing across the globe, but where on the globe is it passing? That's a tough question. Because what the sun sees is it sees this sphere floating out there and says, shadow goes across the Earth. There you go. Have at it. So the Earth, the sun doesn't see what's called what the sun does see is what's called the geodetic Earth. We got any Air Force pilot types in here? No? The pilots are typically the only people who care about the geodetic Earth being different from the geographic Earth. And that has to do with if you're on an F-15 or something like that, and you're flying across the equator, you're not going to fly upside down. The plane is going to roll and be pitched up for the remainder of the flight crossing the globe. And that's keeping track of where is the geodetic equator. Top of the Earth, middle line of the Earth, and the bottom of the Earth. So, given that 39 minutes and 11-second difference from one eclipse, Saros eclipse, to the next Saros eclipse, walking backwards, the path of the umbra across the Earth is going to be, in this case, we're talking about it being in the central region, which means the eclipse is happening somewhere near the node, so it's a pretty good eclipse. And the eclipse is going to shift, since we're starting at the end of the eclipse season, marching backwards through the eclipse season. The next Saros is going to be 1 unit earlier, 39 minutes. And that has the effect of raising the path of the eclipse on the globe. I've exaggerated it here, but it's 100 or 200 kilometers, depending on where we are. We can have another shift. We're marching earlier in the eclipse season, and the path of the umbra across the Earth keeps moving northward. And we'll end up with the path going not only off the top of the Earth, but eventually the penumbra will pass off the top of the Earth as well. And there's we got a bunch of shifts in the location during the eclipse season of the Saros eclipse. And the geodetic Earth is going to show this path that begins at in this case, the south polar regions, marching northward, taking about 1,300 or 1,400 years to complete all those eclipses. Remember, they're 18 years, 10 days apart. And the moon does the same thing. I don't have nearly as good a graphic for lunar eclipses, but it's basically the same effect. Where is the node? Where is the eclipse occurring? So here's the midpoint of the eclipse, but here's the node crossing for this guy. Here's the node crossing for that guy. This guy crosses the node too far away, and we don't have an eclipse at all. Here we go with the Solar Lunar Saros series will contain between 69 and 89 eclipses, each 18 plus years apart, taking 13 to 14 centuries to complete the traverse. There are currently 41 different Saros series in progress. Saros will contain 19 eclipse years, which will contain 38 eclipse seasons, each of which will produce 1 or 2 eclipses of one type or another. There are currently 40 different lunar Saros series in progress. This number 41 is going to end in 2052, I think. And then if we just speed things up and show them all together, we get to see a little bit of an animation here that shows these are all Saros series 145. Finally, totality moves in here. There's a totality moving down the globe. There was our eclipse from 2017, and here we keep marching out through time. And again, notice that we're moving 10 days later, each Saros eclipse. Sometimes it's 11 days, depending on how many leap years are in between. But it's, again, just arbitrary. 6,585 .321 days. And then this ends in 2990, I think. 2991, yeah, there we go. So the last eclipse of Saros 145. And here's Solar Saros Series 139, which is our April 8th eclipse. And I think I gotta stop here. We're about 30 members into that 70 or 71. Most Saros series have 70, 71, or 72 eclipses. Sometimes there's as few as 69, happened once in 5,000 years. It could be 89 that happened twice in 5,000 years. So most of them are 70, 71, or 72 eclipses. Here's our eclipse, number 30. We go on with number 31, marching onward down the planet. 115 degrees farther west each time. And 100 to 200 kilometers. Here's where he's tipped the globe over quite a bit. You see there's the subsolar point way up there. And we finally end. Now I think I can another one here. This just speeds it all up so it makes a little bit more sense. You can watch it spin down the globe, taking 12 or 13 centuries. That's why if I don't see the eclipse on April 8th, I've seen them all. These are all my children. And again, not to be prejudicial, we got lunar eclipses now, so they march into the penumbra, and getting closer, bringing the node closer and closer to the midpoint of the eclipse. Bang, there we go, just a dynamite eclipse, 21 something, which I'm not going to worry too much about. If you watch the visibility charts down here, you can see it steps about a third of the globe each time. I got another one here that marches from south to north. Again, you can see as it marches over 3 times around the globe. And finally, we get here a nice total eclipse, bang, 3 hours of totality. And you see most eclipses are going to be of the penumbral type. Or, in a solar sense, they're going to be most of those penguin polar bear eclipses where you have to go someplace exotic to see it. People just don't do that. I'm going to skip over this one and just use a little bit of time. Now, Cromlin's 29-year cycle ends up being, well, it's 10,571.95 days. 28 years, 345 days, 22 hours, and 48 minutes. Now, the circumstances, Saros, the geometry is almost identical. Saros, or the Inex, not quite as similar, depending on where we are in the Saros series. But we might notice here that the draconic month, there are 388.5011. That's half a draconic month. Which means from one Inex to the next, we're going to have similar geometries, but we're moving from one node to the opposite node. So as we march across the panorama, which we will do with Inexes, we're going to go from node to node to node to node, for what it's worth. And here's how we can see that happening. You can see here the lunar path through the umbra is south of the ecliptic plane, and here's north of the ecliptic plane, but a very similar set of circumstances. Again, here it flips again with one more Saros, or one more Inex into the future. When it comes to solar eclipses, it's less, there's a 2-in-1 cycle going on. It's really hard to describe, but the anomalistic month, back up here, the anomalistic month, 0.67 is about 2/3 of an anomalistic month, about 2/3 the way around. So we have the perigee on the same side of the sun, on the same side of the sun, on the opposite side of the sun. So the velocity of the moon on its orbit is going fast, going slow, going fast, going slow. It's a pattern that really makes it hard to identify the circumstances. But what Crommelin did was looking at Oppolzer's data, he saw this repetition of eclipses. So we can say there is an eclipse, not necessarily the details of the eclipse, but there's going to be an eclipse, one Inex later. What Vandenberg noticed was that, well, if all the eclipses in a Saros series are there, the next inex has another series of Saros eclipses that are all 10,000 days, 28 years, 345 days after the Saros eclipse from the previous inex. So if you take an integer, multiply it times the number of days in the inex, 10,571.95, and add to that some integer, positive or negative or zero, times the Saros interval, you add those together, you're going to get the interval between any two eclipses in time, anywhere. The panorama thus has inexes on the x-axis, Saroi on the vertical axis, and there are no holes in the panorama, and there are no eclipses that are not in the panorama. And introducing the panorama, I'll try to skip through this pretty quick, because it gets pretty heavy. But here we're looking at a very reduced amount of data. Partial eclipses is the Solar Saros series, 145. So this is the date and time of all these eclipses. And eventually we get an annular, followed by a hybrid, followed by a total eclipse. And one inex later, one Saros series 146, you can see from this date 1639 to 1667 is our 28 years, 345 days and some change. So this is what Vandenberg built out of Polzer's data. This is the solar eclipses. Saros series run top to bottom. Whether it's ascending node or descending node depends on that inex value, which is flipping from one node to the next. So as we march across here, inex by inex, we're going from one node, so one set of eclipses are walking backwards this way, the other set is moving in the opposite direction, one inex later. And lunar eclipses, again, not to be prejudicial, follow the same pattern. The lunar Saros series move north and south, the inexes move left to right. And basically Vandenberg took all of the Polzer's data and built the panorama, which I got a picture of it in, I think, on the next slide. But this is an example of what's going on. And what is this? August 11th, 1999, Saros 145, member 21, inex 38 is right here. And we go one inex later, and we get 7/22/2028, total eclipse, Saros 146, one Saros series number greater, member 28, inex 38. If these member numbers are near the same, you're going to have similar circumstances. Because if you look at the entire collection of 70 or 71 eclipses, if the inex values push them too far apart, there's not going to be much similarity. But around the central regions especially, we're going to get a great deal of similarity, but at the opposite node. So this is what Vandenberg built. This is the solar Saros panorama. This is the lunar Saros panorama from the Polzer's data. These two guys just went to town on it, took Fred Espinak's technique and extended it 11,000 years BC, 15,000 years into the future. That's 26,000 years of eclipses. And built this panorama. The Saros goes top to bottom, inexes are moving across, and it produces this really strange curve that is really difficult to explain without bringing other perturbations into the moon's orbit. But John Tilley and Luca Quaglia put this together around 2009 or 2010. An example of how do we get to the next eclipse? We just had one in 2017, and there was an eclipse after that. There was an eclipse last October. How do we get from October's eclipse to our April eclipse? And that's where we're going to be one semester, what it's going to be. And to get one semester, using Vandenberg's formula, we need 5 inexes and 8 Saroi, except now we're going into the past. So we go 5 inexes into the future, about 50,000 days, right, 52,000 days. And then we go 8 Sarai into the past, which is 6,508, that's 48,000 days, thereabouts. Then we end up with the difference between these two, we end up with 177.18 days. And the semester length was 177.17 days. So we went from Saros 145 to Saros 150 because we went, here's our April eclipse right here. We went 5 NXs into the future, and then again, Saros goes from top to bottom. So we go 8 Sarai into the past, and we end up with this really crummy penumbral eclipse in a really bad place on the planet, in Penguintown. So our eclipse right here, this is from what, 2017. The next eclipse was, nobody heard about it or cared about it because nobody really wanted to chase it down there. So if we look at the Saros panorama in detail, here we have green are the, I think I put this on here. Green are the penumbral eclipses because they're at the beginning and the end of the eclipse season, so they're far away from the ecliptic plane. So we start out with green ones and we end up with green ones. The blue ones are totals, the reds are annulars. You can see the red eclipses outnumber the blue eclipses a lot. Hybrids are the yellows, typically the boundary between total eclipses and hybrid or annular eclipses. And I've got Saros 139 running over here just for grins. But we're at number 30 of 71 eclipses in Saros 139, and that is our eclipse for April 8th, 2024, right there. And the next eclipse is going to be 5 NXs in the future, 8 Sarai into the past, and it's going to be up here someplace, maybe a total eclipse, not sure. So the difference between one eclipse and the next eclipse is either what's called a semester, 177.19 days, in this case, or 177.18 is the definition of the semester. And that is, we have an eclipse, or we have a new moon that's suitable for an eclipse somewhere, and then we have 5 new moons in between, and that 6th new moon, we have another eclipse at the opposite node, completely independent characteristics, although it will be related to this 177.19 days. So the only way to get 177.19 days is a difference between the NX length and the Saros length is if we go 5 into the future, 5 NXs, 8 Sarai into the past, 52,000 days, and we end up with a difference of 177.19. This is 66% of the time we have 6 lunations in between eclipses. But every now and then, the eclipse season marches off of where the node is, and we end up a month early. So we have what's called a short semester. The only way to get a short semester is to get a relatively small value. Remember, we're dealing with these big units of time. Yes, that is time. We have to march way out into the future and march way, way back to get a tiny little difference, which will be the quote-unquote next eclipse. So the only way to get 147 days is to go 33 NXs into the past, 53 Sarai into the future from that point, which is, what, 349,000 days to get 147.61 days of short semester, which happens 22% of the time. Then every now and then, when the synodic month fits completely within the eclipse season, that's that 3 eclipse season, 2 eclipses of the same type will occur and separated by 1 synodic month, separation of 29.53 days. The only way to get 29.53 is to get 38 NXs into the future, 61 Sarai into the past, 400,000 days, and we end up with 29.58, which is going to be our separation of 2 eclipses in the same eclipse season, same type. After we have an eclipse, or the semester ones will occur in groups of 6, sometimes 7, but mostly 6. It's called an eclipse set. And the eclipse set will be followed by a short semester, or a short semester illumination and a short semester. Another eclipse set of semesters will follow. Yow, what does that look like? Let's see some pictures. Here's our semester. 5 NXs in the future, 8 Sarai in the past. Here's our April 8th, here's our April 8th eclipse right here. We go 5 by 8, we get an eclipse, 5 by 8, we get an eclipse. If we went 5 by 8, we would have an eclipse, but we're not building the panorama and plucking eclipses out. The eclipses occur and we place them in the panorama. So that eclipse does not occur, well, it'll be on the next slide. The next slide, couple of slides. It's 177.18 days, 6 lunations, 66% of all intervals. Very common. The short semester, we have to go, what is that, 33 NXs into the past, 53 Sarai into the future, and we end up with this partial or annular eclipse right here, after our eclipse from up here. Again, here's our April 8th eclipse, so this one isn't going to happen for a long time. It's at 2025 and 2026. That's not so far away. Right. And here the lunation, 38 NXs in the future, 61 Sarai in the past, and we actually start up here, and we go 30 from our vantage point here. We're at the end of the Sarai series. We go 38 NXs into the future, 61 Sarai in the past, and we end up with this guy up here. That's why we're going to follow a lunation with a short semester, or it has to be followed by a short semester to get us back down to the bottom, so to speak, so we can start marching up through the panorama. And here's our eclipse set, marching 5 NX, 8 Sarai, 5 NX, 8 Sarai, 5 NX, 8 Sarai. Boom, 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 boom. And we would march off the end here, but again, we don't. We run into a short semester is what happens. I think that this is an animation here. So here is our April 8th eclipse. Yeah. We are in the middle of an eclipse set. So we got 3 more eclipses in this eclipse set, which gets us out to 2025. Remember, these are the quote-unquote next eclipses. Next eclipse season, about 6 months apart. From there we have a short semester, gets us back down here, where we have another eclipse set. Bang, 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 bang. Gets us out to 2029. And here's where we have a short semester followed by a lunation, which gets us back to the top down here. So this eclipse, 6/12/2029 and 7/11/2029. You can see they're only a lunation apart, 6/12 to 7/11. And again, this one, there's 3 eclipse seasons. One's at the beginning of the eclipse season, one's at the end of the eclipse season, whether it's this way or this way. They're far from the ecliptic plane, and they're not great eclipses. So here we are way down here, and we end up here. But being up here is not going to do us much good. So we need another short semester. Gets us back down to the I can't tell you whether that's the beginning or the end of the eclipse season or the Sarai series, because I don't know whether it's an even number or an odd number. So it's whether it's at the ascending node or the descending node. But we're going to follow it with an eclipse set, and obviously we're marching back towards the beginning of the eclipse season, back towards the Sarai series, I should say. And then we have a short semester, followed by an eclipse season, followed by a short semester, an eclipse set, a short semester, followed by a lunation, which gets us up there, and then we come down with a short semester, followed by an eclipse set that gets us to, you can see right here, those 2 eclipses stacked on top of one another are in the same Sarai series. So there's our next eclipse of this Sarai series in April 20th, 2042. 18 years, 10 days, or 11 days off into the future. Intervening eclipses from one Sarai series, first and last. Here are the eclipses in their text being peeled off, actually creating the panorama. So there's 41 eclipses in this set, and we'll end up with duplicating, where's our guy, right here? Nope, sorry, it's right here. So there's only one place in this entire sequence where there are 2 eclipses in the same Sarai series, 18 years apart. So these are all the intervening eclipses during the 71 eclipses during that Sarai, sorry, it's 41 eclipses during the Saros pattern. So here I just took 113 years with eclipses, 257 eclipses, and how it marches across the panorama. You see, it's just peeling off, marching sort of on a diagonal, but it's not missing any, and it's putting into this. These guys are kind of weird. I'm not going to try to explain those. But that pattern of short semester, lunation, semester, 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 short semester, 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 that is not infinite. Every now and then it's like, oh, let's throw an extra lunation in here. So there, the Saros 117 will end August 3rd, 2054. If that means anything. Vandenberg looked around and said, oh, I can predict eclipses by using the panorama. You go so many NXs in the future, or in the past, so many Saroi in the future or the past from that point, and you get another eclipse. Maybe it's got the same geometry, maybe it doesn't. It depends on what it is. So we've got, this is better on the next page, actually. So he came up with the hexon, the hepton, and the octon, which get their name from the number of semesters that are involved with those intervals. The SAR is very important. I'm going to talk about that in a minute. I don't think even Vandenberg knew about the SAR. The tritos, the thix, and the triple tritos came from the Mayans. They had intervals as well. Here we have the NX, and the Saros is in here doing their thing. And the exolithmos, of course. And what do they look like? The hexon looks like this. If we go, what's it, 8 NXs into the past, and then go 13 Saros into the future. So we have to go this way, this way, this way, this way. And the two eclipses prior to our April eclipse are these two up here. The hepton, 1,200 days. What is that, 41 to 70 eclipse season, 3.5 years or something like that? And we bring the eclipses are seemingly closer together, but they're actually farther apart by the number of days, because we have to march up, come back down, and then march up the next row over to catch up to one of these hepton eclipses. And the octon, 2 NXs in the future, 3 Saroi into the past, and we're going click, 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 like that. And this is our April 8th eclipse right here. The SAR, the half Saros. How do you step a half Saros? I'll come back to that. The tritos, 1 NX minus 1 Saros. That's 45 degree angle, but it's almost 4,000 days. That's, 11 and a half years, or something like that. Then our Saros, we know all about the Saros. This is the eclipse set that belongs to our eclipse. 7 eclipses altogether. The fix, 9,300 days, that's what, 27 years, 26 years or something like that. And triple tritos, 11,959.89 days. With all of these, it's fractional day. It's an approximation, but it's a real close approximation. Off by, in this case, we'll only go on 69 eclipse seasons, which is what, 33 years. We're probably off by about 2 or 3 minutes from when the eclipse actually occurred. And the SAR gets us from solar eclipses, steps into the lunar eclipses. Because we're stepping a half lunar orbit, we're moving from one node to the other without moving the sun. And we end up with, well, a lunar eclipse instead of a solar eclipse. So here's our 2024 April 8th eclipse that we're going to enjoy so much under the clouds. And 2033, April 14th, this is, you can picture, here's the subsolar point, sort of the geodetic equator. Here's the midpoint of the eclipse north of the subsolar point. Here we see the path of the moon across the umbra north of the center point, midpoint of the eclipse. Lunar eclipses, I'm not sure why I have this in here, but it's just, here we go from 1900 AD to 2100 and all the eclipses that we're going to be covering. Now this is the solar eclipse and then the lunar eclipse 1 SAR later. actually, the lunar eclipse starts first. So the lunar eclipse has a date, and the solar eclipse is 1 SAR, 9 years, 5 days later. And you can see the geometry between those two are so similar. We're starting at the south polar region here for the solar eclipses. We started south with the penumbra and umbra for the lunar eclipses. And as we're marching up into totality here, for the partial eclipses, we end up with the umbral path across the globe. And here we march through the central eclipses, and then we march up towards the top. And eventually, when we run out of umbra, we're going to run out of totality over here. Right there. Oh, oh, there we go. Hold on. And we end up with, in this 9 years, 5 days apart, across 13 centuries. So, wrapping things up now. I'm sure you're happy. Your chairs don't squeak enough. That's what it is. Like the squeaky chairs. 2024, that's our eclipse. 2045 is the next really good one in North America. Well, maybe.
Look around there. Not high probability, yes, sir.
I have great faith in modern medicine. 2052, there's another one that just cruises across Georgia and the Carolinas. And 2078, another one in the southern, southeastern United States. And again, lunar eclipses, a few good ones. The ones that are owned by these solar eclipses. There they are, 9 years, 5 days apart from the solar eclipse. But it's a chicken and egg kind of thing. The lunar eclipse precedes the solar eclipse. The solar eclipse precedes the lunar eclipse. So they really are in between one another. It's the best way to think about it. Craig Nemi, who was the director at the observatory back in 2017, said, well, when's one going to go across the observatory? We don't have to go anywhere. So when I'm looking, and there aren't any. There's some to come close. Even for you guys, this one misses. 2099, it's an annular eclipse that moves, no, it's a total eclipse, sorry. It is a total solar eclipse, moves across central Ohio. 2121, there's another good annular eclipse that goes across the United States between Louisville and Cincinnati. So it's a short drive to get to that one. Now, 2121, I do have problems with that one. 2153 goes over Louisville. Again, you guys get shut out, but it's a short drive to get in there. Or whatever we're doing, jetpacks or whatever in 2153.
Mule carts.
Personal drones, yeah, that's it. April 12th, 2154, an annular eclipse comes across the United States and does go right across Cincinnati. You guys are in the penumbra. The observatory is right about there, so it's not really directly over. That was the best I could do. March 30th, 2052, talk about that one, these are the circumstances. Now it's going to cross Florida, Georgia, and South Carolina. Here at 2045, this is the next one of Saros 136. It's the next good one across this part of the United States. You can see it does hit California over here, and who knows if it's California still going to be there. Here's our 2017 eclipse, what it looked like here at Hopkinsville, right about here. And the greatest eclipse and the midpoint of the eclipse are in two different spots. It's got to do with the movement of the moon on its orbit. It's not just moving the path, it's the Earth is rotating as well. April 8th, 2024, here we are. Zoom right across here. Here's Dayton, Springboro, or Miamisburg is right down here somewhere. Down there. I am going to be in Batesville, which is right about, where's Batesville? 74. Batesville's right that way here. So I'm going to be there. 2 minutes and 54 seconds of totality there. You guys here have what, 2 minutes and 2 seconds of totality, something like that? And I came across this diagram, which said, now if you understand this diagram, you've just collected all the information you need from the last 2 hours. if you are interested in this data or anything else, eclipsewise.com and astropixels. Eclipsewise.com is Fred Espinac. All his data is available there. Astropixels, there's a great deal more data out there as far as node passages and perigee passages, and it's just a real treasure trove of data. Again, because the government paid for it, it's yours. Archive is where you can get all kinds of papers and other information about eclipses and just about anything that has to do with astrophysics. Eclipse.gsfc, that's the Goddard Space Flight Center, nasa.gov. This is Fred Espinac, but it's the NASA presentation of that data. And of course, Wikipedia. Careful with Wikipedia. You've got to find something in 3 different places before you believe it to be true. 20 years ago, when Wikipedia was getting started, it was terrible. But they've cleaned up the editing capability quite a bit, and there's lots of good information out there. And then solarsystem.nasa.gov, this is kind of a pop site. Eclipses will show you all about the lunar eclipses that are coming up. And there we are. A couple of lunar eclipses going on. Phew.
Oh, thank you.
Thank you for putting up with this.